We've discussed how to compute a householder transformation, H, such that H times x is equal to plus or minus the 2 norm of x times the first standard basis vector. And here we're just talking about the real valued case for simplicity. And we restricted our householder transform to have the form I minus 2 times u transpose. Again, let's just focus on the real valued case. And what we saw was that the way to compute this was to set v equal to x minus plus the 2 norm of x times e0, where if you pick the plus here, you would pick a minus here, and if you pick the minus here, you pick a plus there. The question might be, which of the two should you pick? Well, let's have a look at what this looks like. Well, if we write x as chi0, chi1 through chi m minus 1, then notice that this is just an adjustment to the first entry in the vector, so this is minus plus the 2 norm of x. Now, if the magnitude of the vector is mostly concentrated in chi0, then the magnitude of chi0 might be almost equal to the 2 norm of x. In particular, if chi0 is approximately equal to the 2 norm of x, then subtracting off the 2 norm of x might create a situation of catastrophic cancellation. Notice that we can easily avoid that by saying, oh, if chi0 is positive, then we should add the 2 norm of x, because then you're adding two values of the same sign, and that automatically avoids catastrophic cancellation. Alternatively, if chi0 is approximately equal to minus the 2 norm of x, then you would want to subtract off the 2 norm of x, because again, that means that you're adding two values of the same sign. So that tells us how to compute that, and you actually need to be very careful with that, because if catastrophic cancellation happens, then the net effect of that is that the mirror is not being placed just right, and that then means that the householder transform is not quite the one you want. So this is actually important. Alright, now there's a second detail. So far we've always talked about I minus 2u u transpose, where u then is computed from v by taking its absolute value and dividing by that. Right? Now, alternatively, you could say, well, let's not do that. Let's instead define our vector here as any vector u. We're going to show how to compute it from v, but instead of formulating the householder transform like that, we're going to formulate it as I minus u divided by the 2 norm of u, with a 2 here times u divided by the 2 norm of u transpose. And it's pretty obvious how to generalize that to the complex case. Now we could take u to be in the direction of v, but scale it any which way we want. Well, you shouldn't scale it by 0, but other than that you can pick any scaling factor you want. This then is equal to I minus 2 u transpose over tau, where we pick tau to be equal to u transpose u divided by 2. Okay? Now, you can ask yourself, all right, now we can scale v any which way we want in order to create a vector u. What's the best choice? And it turns out that for practical reasons, the best choice is scaling v in such a way that this entry here becomes 1. Now, why is that? Well, let's start calling this vector u here the householder vector. It's really the vector that defines the householder transform. We'll call it the householder vector. Notice that as we compute the QR factorization, we would want to store these vectors u somewhere. Because eventually we want to accumulate all of these unitary matrices into one matrix Q. Alright, so how does that work? Well, if we choose to scale V in such a way that the first entry is equal to 1, then we can take the rest of these entries, which have been divided by this first entry, and store them over all of the entries that have been zeroed out in the process of computing the QR factorization. The 1 we don't need to store because we implicitly know that it must be equal to 1. That now becomes our convention. Finally, tau can always be computed from how you chose your vector u, but it turns out that it's actually better to store it so you don't have to recompute it every time. Anyway, we're going to now see how all of these little details allow us to now compute the QR factorization via the sequence of household transformations being applied to the matrix A.